Okay, let's get started. So before, talking about going to the lecture content. Yeah, so I think 2 more lectures are left, including today. And then there's the exam. Unfortunately, I have to do exam, even though I don't want to do that. So exam is the rule is it's Kaijuan, but you can bring your iPad or notepad is okay, but not laptop, and you cannot type. You have to switch the internet off for tablet computer. So it's only for reading PDF. So you cannot click and so on. It's okay for using iPad or tablet. That's okay, but you cannot type. You cannot connect to internet, and that's a rule. Or otherwise, whatever book you want to bring, whatever. No, I mean, I just so stupid that you just print out my lecture note, 100 pages lecture note, and then everybody print out and so on. It's so stupid. So it's okay to use the tablet computer or notepad is okay, but do not type. That's a rule. And then most likely, I don't remember, 28? I don't remember. Today is 14 plus 14, 28. Okay. 28 is the same time, I think, and yeah. And what's the rule? And then I started creating a exam problem. 2/3 are 2-dimensional CFT. The 1/3 is the higher dimension, and then so that's the rule. Any question about the exam? Yeah, and then what is the final? Final grade will be. I'm still wondering. It's homework is. My plan is homework is 60%, and then the final exam is 40%. That's my plan. But maybe I don't know. It depends on how. Maybe it may go to half and half. But my plan is still like 60 to 40. I may change my mind, but that's my plan. So still important. Anyways, nowadays, I think from now it's gradually much more important exam than homework, because now there are lots of things going on, and this AI stuff is going on. So using AI homework is easy, becoming easier and easier. But my lecture level still AI does not catch up, I hope, but still useful. But anyway, so that's my percentage for the final grade. And then right after the exam, I will grade your final exam with my TA and submit the final score to the department. So if you don't submit the homework, or some of your friends do not submit the homework, you guys should submit before final exam. Otherwise, your score will be affected. So if some of you, I think most of you here, present here, is okay for homework, but your friend, somebody you know that who registered the course, who does not submit the homework, you should suggest him or her to submit the homework. So that's it. I think that's the rule. Any question about the exam? Okay, if not, let's get started. Yeah. Maybe the rule is, okay, so then let me write that rule of the chain function. Is the no internet, no type, but can bring node part or iPad, not like a computer, the laptop type. It's not not like this DNL type. Like this type is okay. And to read PDF file. That's only that PDF file. So before the exam, you should download all the PDF file you want to refer to. Then after you start, before you start the exam, you have to turn off the internet. And then if you type, anyway, this is very strict rule. So if you break this rule, I have to give you F. I have to give you, but I don't want to give you F, so please follow the rule. I don't want to give you F and so on. So those are rules. This is the rule. And at the same time, same rule. Okay, so that's of course, book is also okay. Anyway, what try is different. Okay. So that's a rule. And then let's go up to the content of lecture. So we're talking about some correlation function of the higher spin primary field. And last time I briefly wrote Takahashi identity approach. And then today I'm going to talk about the embedding space-time formalism. So today, so first I recap and correct with correction first. And after that, I'm going to talk about embedding formalism. So this one is very kind of like a very computation friendly, and also, yeah. So the correlation function we are looking at is something like a spin one and 2-point function primary. Primary 2-point function. That's we are looking at it. And then so we try to obtain something like a JMU of x1 and JMU of x2 at this correlation function, this. And then what we saw before is that so under the conformal transformation, so we looking at the conformal transformation is something like so conformal transformation is x prime of x is equal to I times E plus lambda inverse H I of x like this way. So what we did is this is E here and this is 0 here. So what we did is the first we take the so point inverse of x. So start with x here and bring it to I of x. So this is inversion. So I of x is x over like this way. Okay, then take the difference between 1. So that is this quantity, and do the rotation. Rotation is like h of like this way. Is h of like this way. And after that, you do the scaling. Scaling is something like from 0 to like this way. Most likely what I'm saying is not correct. So if you do the h, still the point should be here. And then scaling is like this way. So lambda inverse here. And after that, you shift by 1. So that's a shift by 1. And then inversion. Take inversion by here. Something like this. This is the experiment. So that's a transformation we did. Okay. Those are all. So composition of the all the conformal transformation we look at. Okay. And then this one, if you 0 and E are fixed under this transformation. I of E is E, E minus E is 0. So this point is fixed up to here. I mean, always fixed under any transformation. Okay, any transformation. So I of E is E minus E is 0, and then 0 of rotation 0, and the 0 of scaling is 0, and you shift by E, and then inverse. So E is fixed. So this will fix E and 0. So the other is 0 goes to infinity. I of 0 is infinity. Infinity minus E is infinity. Infinity rotation is just infinity. Scaling of infinity is infinity. The shift by 1 of infinity is infinity. Infinity of I is 0. It's just mapped to 0. And then if you look at the infinitesimal transformation around the so that's the case. And around here, the point x is in fact behave like something like a lambda inverse. Like this. So IE is the delta mu minus E mu, and then as far as I remember, there are 2 here. So that's the case. This one is the infinitesimal version of the this I. So the I of x mu is x mu over x, and the del I of del x mu is x mu minus 2 times x mu like this way. X squared. So x squared. Okay, so that's the case. And then, so if you plug into the x is equal to E, so it becomes like this. Moreover, if you're looking at the infinitesimal transformation around the 0 point, so x prime of x will behave like a lambda h of x. So that's what's really happening. I mean, essentially this point is mapped to close to infinity. If you go to close to infinity, the shift of E doesn't matter, and the rotation doesn't matter. Rotation matters. Only rotation matters. So that's why h is here. And because of inverse, lambda goes to there is no. That's what's really happening. And then, so this spin 1 operator also behaves similar way around the 0 and the E here. So you can scale, as I mentioned previously, this one can scale like something like this x1, 2, and then 2, delta 1 plus delta 2, changing of theta, changing of E, something like that. Okay. Okay, I think x hat is the x1. And you can rotate this x hat to this point around point 1. And at the end of the day, so what you really have is that under this transformation, J mu of 0 and J mu of E is transformed. And yeah, so this one is lambda 1 minus lambda 2. So lambda 1 is of course this one. Conformal dimension has lambda 2. And then you have the representation of the H inverse, H. I think it's opposite in the case. Lambda 2 minus lambda 1 inverse. Yeah. So essentially what you have is that the H mu rho and then I E H I E u sigma rho 0 J sigma. So this is the transformation under this transformation. This 2-point function transform like this. Since it's spin 1 field, it's really behave like as coordinate. It's as a coordinate like this one. And so then I think we should be okay. 1 minus 3. And then, so it's a conformal field theory, so it's invariant under all the conformal transformation. So, so therefore, under this composition conformal transformation, it should be invariant, which means that the lambda 1 should be equal to lambda 2. No, lambda. Delta 1 should be equal to delta 2. So, as before, the spinless primary field, the 2-point function is non-vanishing when lambda 1 is equal to lambda 2. And then also this quantity, under this quantity, so this means that the last time I explained, so if you set, so this means that so this J mu of 0, J mu of E, then this should be proportional to some constant times I mu. So that's the, if you set this one, this condition satisfies. Okay, so therefore from here one can show that this one is equal to J mu of x1, J mu of x2 is equal to, or maybe 0 is okay. I mean, well, it's okay. x1, x2, then the x1, 2 to the 2 delta over c1, 2. And then delta mu minus x1, 2 mu, x1, 2 mu, and the x1, 3. So that's the correlation function at times 2. So that's the what Takahashi identity will tell us about. So of course, I mean x1 2. That's the words of Takahashi identity will tell us about two-point function of the spin 1 field. Therefore, so this one, or usually people set the x1 to be 0. So if you set the x1 to be 0, this one is c1 2 delta mu times 2 x mu first this way, and this one we call I mu. So that's the case. And then similarly, we can do the similar computation for the higher spin field, mu L of 0 or mu 1, no, mu 1, mu L of x. We can do the same method to determine. And we assume this is the, again, symmetric rank L, symmetric traceless tensor. Primary tensor. Then this is something like a proportional to some constant divided by x times 2 delta I mu 1 I mu L, and then symmetrize it, and mu 1 mu L symmetrize it. And then minus traces. Traces means all the mu and nu are, sorry, traces mean mu and mu 1 and mu 2 if you just take a traces and so on. So for instance, so this means, so I call it this one is symmetric traceless of I mu 1 I mu L divided by x2 delta. So that's the word Takahashi identity will tell us about how this higher spin field should behave. Two-point function of higher spin field should behave in conformal field theory in any way. So notation of sim A mu 1 and B mu 2 is essentially A mu 1 B mu 2 plus A mu 2 B mu 1 divided by 2 minus taking trace A dot B and the appropriate power over D delta mu 1 and mu 2. So that's a notation. So, and then it becomes traceless. So here, sim means the trace is symmetric under this indices mu, upper indices and lower indices, each of them. So that's what I mean. So yeah. So if you take a contract with delta, say mu 1 and mu 2, with this guy, sim A mu 1 and B mu 2, then this is equal to 0. So it's a traceless. And also, obviously, it's symmetric. Okay. Any question at this point? Okay. So this one, I mean, here we need to use some analysis of the word how these 2 points behave under conformal transformation. Okay. Under the conformal transformation, some special conformal transformation, and then to determine the two-point function. So that's one way to determine. Another way is embedding spacetime. So that's I'm going to tell you today. So yeah. So this when Takashi symmetries manifest are computationally difficult. But so it's so 2011. So people invented many I don't remember who. Yeah. So there's the embedding space formalism. So this one, so we embed the since the so if you start with the d-dimensional CFT, Euclidean signature. So then, what is the conformal group? Conformal group is SOD plus 1 and 1. Okay, and then so we embed the space-time. So we consider the Lorentzian symmetry in D plus. So you just this is of course the acts on the Lorentzian symmetry in D plus 1. So this is the D plus 2 Minkowski dimensional Minkowski space. And then we use something called light component two new light component. So I call this space is the I call this one is the say x minus 1 x0 and x1 xd. So that's the coordinate notation, and then we introduce something called the light coordinate, something like this way, where the x plus minus is given by x minus 1 plus minus x0. Okay, so that's the light component we introduce, and then so therefore the Minkowski signature is something like a d x minus 1 square plus the dx0 square plus plus the xt square can be written. So this part can be written as plus minus 1/2 dx plus dx minus, and then minus 1/2 dx. No, it's okay. And then the rest is just delta mu dx mu dx mu. So that's the metric one can write down like this. Okay. So here it's two light components. So this is the light component. Coordinate. Okay. So you just read that. And here, so first, to preserve this symmetry, so we just assume that all the vector First of all the vector is the light cone. So here you have the x minus 1 direction, and say x0 direction, and then x1 to d direction, and you just consider right cone. Sorry, my right drawing skills not good. Like this way. So you just consider the vector on here. So always vector is something like here, so that the x squared is equal to 0. Suppose x squared equal to 0. And then our space-time, so for instance, x, if this condition is satisfied, automatically satisfied if you pick xa is equal to lambda times 1 x squared. So this capital X is something. This is a capital X, small x, x1. Okay. If you set this one, so here I use the small x for d-dimensional CFT coordinate. So this one is small x, 1 dot small xd. So those were Euclidean coordinate. And if you embed this RD inside, so we want to embed this space inside this light cone coordinate, and some slice of light cone coordinate. Okay. And this slice is specified when lambda equal to 1. Okay. So here you have the light cone means that this condition will kill 1 degree of freedom in this coordinate. Okay. So therefore it's d plus 1 dimension hypersurface. Also there is a singularity here, and furthermore, and this d plus 1 coordinate is lambda, and then d-dimensional coordinate in here. Okay, and as you can easily see, if you plug this one into here, you can easily see that the x squared is equal to 1. Okay, so you can easily see, right? So okay, maybe I can explain. Okay, so in this space matrix, so the matrix is given by as follows: 1/2 A plus B minus 1/2 A minus B plus A mu dot B mu. Okay. So that's the inner product from this matrix. From metric comes from here. So therefore, x squared means that the minus 1/2. So let's see. 1 times x squared minus 1/2 x squared plus x mu. This is equal to 0. You can easily check times lambda for this embedding for light cone. So this is light cone coordinate, and in particular we can set lambda equal to 1. If you set lambda equal to 1, that is really embedding of d-dimensional CFT inside here. And there is a slice is written in the original paper, which I forgot to write down in the lecture note, unfortunately. Anyway, so let me check. Original paper is still like this one is 2011, so it's still new. I think 2011, you guys are still like whatever's like middle school students or something like that, or maybe elementary school student. I don't know. Something like this. Still quite recent. 2011. Yeah, most likely somewhere between it. Elementary school. Yeah, Costa, Panedones, and Poland, and Richkov. And unfortunately, I forgot to draw the original figure. Yeah, I thought that it's written in somewhere. Oh yeah. So yeah, the space-time slice is the something like this one. So this kind of slice you can take for RD. So RD is embedded in this slice. Okay. In this slice. Okay. And then using these embeddings, one can try to compute the correlation function explicitly. So, okay, and then, so to do that, so there's a four principle one can do that. So first of all, so given a local operator phi, let's say nu one dot nu L, and then x mu is the corresponding to the, sorry. It should be okay. I think my election of the label is something strange. It's mapped to the operator A1 dot AL in this higher dimensional. So this is D plus 1, D plus 2 equals the operator. Okay, maybe this is the operator in this R, D plus 1 dot 1. So this is the operator in R, D. Operator in the R is mapped to this way, and then so we assume this coordinate x is, so the first assumption is the, so we map this operator like this way, and then assumption is y is x squared is equal to 0. Second, and then it's homogeneous in degree, yeah. So it's just compound dimension. L of x, lambda x. So under the scaling transformation, it just gives you the same scaling dimension as original operator. So this has the compound dimension. So this has compound dimension down. Like this. And then number 3 is that so this is the this is actually, so these are representation. So these indices. So number 3 is these are representation. These indices are universal representation. Direct of SO E plus 1, 1. So in this lecture, we always assume this is so include a symmetric traceless rank L tensor. That is the earliest representation SOD. And we also always assume this is the case in this lecture. So because for the sake of simplicity. And then furthermore, we assume that number 4 is the assumed XA, and then is projected by, is orthogonal to these X, the position. So these indices are orthogonal to so there is a transverse condition. This is called transverse condition. So we assume this condition. So to determine the correlation function of primary field with highest field. And then we will use that consider this so here we first assume this is the primary operator. And what we need to do is the pullback, and the coordinate is always assumed to be the XA is the lambda 1 X squared and X cubed, and eventually we fix lambda equal to 1. And also we will pull back to the original slice. So here we assume that the position operator always the high dimensional operator is the same. Embedded into this phi A1 dot AL like this way is here is the of X. Position here, X is here on the light cone. And this indices is the somewhat orthogonal to the So these indices is always projected by, if you contract with any indices, is C. Okay. So that's the condition. And then to prove out the original RD operator, so we will do the following the pullback. So that phi mu1 dot mu L of the X is given by as follows: del XA1, del small x mu1, so del X L small x, del small x mu L, and the phi A1 AL of X, or capital X. So this is a pullback from high dimension to low dimension. And let's look at the one of the cases, this one. So this one, del capital XA and del small x nu is given by 0, 0, and 2x nu. And then delta A like this. So, and of course here we set lambda equal to 1. So here, if you set lambda equal to 1, derivative of small x is 0. Derivative of small x nu will give you 2 times x nu, upper nu. And derivative of small x mu by x nu will give you del n. So that's the case. Maybe, yeah, I think I should write down this one. I don't know how to phrase this one. Yeah. New is bad because I use this new here. Anyway, so that's okay. And let's compute the using this rule to compute two-point function and the higher point function. Okay, so that's the case. And as far as I recall, so this lambda equal to 1. So this lambda equal to 1, lambda equal to 1 is called Poincare section. Poincare section. So this part is called Poincare section. It's called Poincare section. So let's compute consider simplest example. Again, two-point function with spin 1 field. Okay. So to construct the SO d plus 1, comma 1 invariant, so this should be function. This should be function of x1 dot x2. Okay. Of course, the inner product is invariant under the SO d plus 1, comma 1 transformation. Furthermore, since phi AI lambda x is the lambda minus del I of phi AI of x. So therefore, this means that this should behave as follows. So from this analysis, this will tell you that this should behave under the this is behave under some constant times minus 2 x1 dot x2 times the delta 1. Delta 1 dot delta 2. So this is the only form one can consider. Okay. Can you see that? Is it okay? So for instance, if you map lambda, so for instance, if you map lambda goes x1 goes to lambda x1, okay? So this correlation function should behave like a lambda minus, like this way. Should behave like this way. On the other hand, x2 map to lambda x2, okay? Then it should behave like this one should behave like a lambda minus delta 2 is original one, okay? But since it's a function of x1 dot x2, okay? x1 the x2, you have to treat x1 and x2 equally. So the scaling of x1 is equivalent to scaling of x2, okay? So therefore, this scaling should be the same as this scaling, okay? Do you understand what I mean? Is it okay? Since it's a product of the x1 and x2, it's just an inner product of x1 and x2. So we should treat x1 and x2 equally. Scaling of a lambda goes to x1 goes to lambda x1 is equivalent to x2 goes to lambda x2 at the level of correlation function. Because it's the inner product. You multiply lambda x1 is the same as The multiply lambda x2, same thing. So therefore, this scaling dimension should be the same as this scaling dimension. That it will give you delta lambda 1 and lambda 2. Okay. Furthermore, to have this scaling under this transformation, it should be 1 over this quantity. Okay. That this minus 2 is just a choice. I mean, you can just have. So now we try to pull back this answer by using this method, this pullback. Okay, so let's try to pull back. What's this? Capital X1 dot capital X2 is equal to so if you write down, so capital X1 is the 1 small x1 square and then x1 mu, and the capital X2 is 1 x2 square and the x2 mu. Okay. Therefore, this product is given by 1/2 x2 square. Sorry, small x2 square minus 1/2 x1 square minus the plus x1 dot x2. So that's the, if you write down in terms of coordinate, in terms of this embedding, this Poincare section, this inner product is given like this. And this is exactly minus 1/2 x1 minus x2 squared. Okay. Plug that one into over there, you can see that so this small phi of delta 1 x1 small phi delta 2 x2 is equal to constant times delta 1 delta 2 times x1 minus x2 times 2 delta. So that's exactly, so if you plug this one into over there, you can find such a conclusion. Okay, so that's how you did a computation of this. Sorry, I think I think it's not A, so this is delta. Sorry, this is delta. That's what I meant, delta. Sorry, this is delta. So I think it's just scale up here. It's just scale up here. I think, yeah, sorry, it's delta. So this is a scalar 2-point function. That's how you compute by scalar 2-point function in the using the embedding space formalism. We can do the same thing for the 3-point function. 3-point function is equivalent. Scalar 3-point function. 3-point function. Let's consider the following thing. Then again, in order for the this guy is this Lorentzian invariant, so the constant it should be something like a -2 x1 dot x2 and a12 and -2 x2 dot x3 a23 -2 x3 dot x1 a31. So that's the generic form for the 3-point function to be this Lorentzian invariant. Okay. So those are non-zero. So the x1 dot x2, xi dot xj is non-zero Lorentzian invariant quantity. So this is the most generic choice. And then again, if you use this rule, so x1 goes to lambda x1 will tell you that the a12 plus s31 is equal to lambda delta 1, and then a12 plus a23 is delta 2, a23 plus s31 is equal to delta 3. So that's the immediate consequence of the scaling transformation. That's you can easily see. But you just multiply lambda for x1 coordinate. So x1 coordinate is a12 and a31. That's why you get this left hand side. And then if you scale x2 coordinate, you see x12 and x23. And that should be equal to delta 2, and so on. So you can just a12, a23, a31 are the unknown variable, and you have a linear equation you can solve it. But you can easily see that the a12 is the delta 1 plus delta 2 minus delta 3, and so on. So most likely I should write down cyclically I plus 1 is delta 1 I plus delta I plus 1 minus delta I plus I is most 3. And then you do a similar calculation. So we can use this fact. The inner product is just the difference between in the d-dimensional CFT coordinate, so that the plug that went to here, you can recover the what we have already know. So this means that the phi 1 is the x12 and x12 divided by 2. I told you, divided by 2. And then x23 delta 2 plus delta 3 minus delta 1. And x31 delta 3 plus delta 1 minus delta 2. And so the important thing is that if you use this embedding, so this inner product will become difference between the coordinate. That's important. So those are scalar coordinates. Now let's move on to tensor one. So for tensor one, so this one is becomes very important. Number 4 is conjugation is very important. So let's consider the following operator. So again, symmetric rank L, symmetric, traceless, tensor field. So here, let's see, phi and L of x, x1, and phi and 1 also the NL of x2. So if we consider this high-dimensional case, again, so to have a Lorentz inverse, it should be function of the x1 and the x2. And of course, if you do the same manipulation, it should be proportional to delta and some constant times delta 1, delta 2. But now what we want to say is something about these indices. And then now we can use this property to say something. Okay. So here, so this correlation function. So if you have x and 1, x1, phi state. Like this one is equal to 0. And also we can do the same thing. If you multiply x2 dot n I is also with this one is equal to 0 because of this transverse condition. Okay. So to achieve this one, and then it should be Lorentz invariant under SOD plus 1 from 1. So the invariant basic tensor we can construct is something like this one. Is the x1 and x2 is something like this one. Beta m minus x1 m x2 m divided by x dot x2. So that's the basic tensor we can construct. Okay, so it's for the sake of the simplicity, yeah. So then you can see that the inner product of the x1 of I, so I don't like x1, so let's call this one is x and y. So then I think it becomes very simple. Okay, so that's the oh, there is something strange. Okay, I'm sorry. So there's a typo in my lecture. So then you can see that from here, you can see that the xn dot imn is equal to 0 because I mean, okay. Maybe I should. Oh, it's okay. It's okay. What I wrote is not correct. Here. So y and x. So x is correct. So then xn is xn minus x dot y, yn, x dot y, and this is equal to 0. The same thing, yn, same reason, is equal to 0. So yeah, so if you contract with x and y, you have an inner product cancel, and that will give you b. Sorry, it's xn minus xn. So therefore, this tensor will satisfy this transverse condition. Okay. So therefore, one can show that since it's a symmetric traceless tensor, so therefore what we expect is same is the I m1 n1 x1 and x2 and L x1 y1 and this should be done. So this should be done. And now we try to pull back to the d-dimensional CFT. Okay. Now we pull back. Okay. So now, when you do the pullback, so I mu nu, I mn, so I mu nu is delta capital Xm, delta small x e. And I. Okay, so that's the pullback problem. And then what we have is as follows. So this one will give you the. Okay, well, what's this? So we know this one is the. So let's take xm is the what's that? 1x squared. 1x squared x mean. But yn we take the following coordinate. Y squared over 2, y½ and y mean. Okay, so if you take like this way, so what we have is as follows. So this one is equal to del xm, del small x mu, del capital N, del small y mu, and then A and N minus ym xn y dot x dot y, like this way. And we know the x dot y is given by what? So let's compute one by one. Okay, let's compute one by one. So let's compute x dot y. This is equal to what? Minus 1/2. No, I think I'm doing something strange. Why I'm doing like this way? So minus. Just a moment. Sorry, I didn't. Something strange. I don't know why I use this. Something wrong with this. So what I wrote here. Hmm? Sorry. Let's do one by one. So del x n del x mu and yn is 0 x mu 2 times x mu and then delta mu. Okay. So times this is something strange. Yeah, I think something strange. So what if I write as before? It should be okay, right? This should be okay. Then this should be 1 y squared, and then y. Okay, I think this should be okay. This should be okay. Sorry, 1/2 and 1/2. Is that what we need? Sorry, I got confused. So this should be equal to. No, it should be okay. There is no 1/2 is okay. And this is just x mu minus y or plus y mu. Is it okay? Y mu. It should be okay. So what I wrote here is something strange. It should be different as before. Okay? So that's the thing. And similarly, okay, it should be okay. Yeah. Similarly, so this one. So therefore, what you get is as follows. So this one will give you delta mu nu, and x dot y will give you x minus y squared minus 1/2, right? Minus 1/2, and then minus 1/2, and here this one times this one, and this one times this one will give you, what was that? So x mu minus y mu. and the opposite, x mu minus y mu. Okay, so everything okay. So now it's okay. And this is equal to delta mu minus 2 times x minus y squared. You have x mu minus y mu, x mu minus y mu. And this is I mu x minus y. Okay, that's what we said. Okay, so what I wrote here is not correct. So this is the correct. In the direction of this, there's a typo. So this is as before is okay. And to get this one, Okay. So therefore, if you use this pullback method to compute this quantity, you get the original one, and plug that one into here, you get the previous method. Result obtained by Ward Takashi and it. Okay. Any question at this moment? So do you understand this one? Is it okay? I don't think I made a mistake. So the lecture note is not correct. So I think this is the correct way of doing it. Any question at this moment? So therefore, if you use this the embedding space-time method and construct this basic tensor here, one can use pullback to get the previous. Okay. So that's the nice part of this convenient part of this method. Okay. Then let's take a break. 10 or 15 minutes break. Yeah. Sorry, I made a mistake. A lot of typo in my lecture. I don't know. I cannot open. Can you open overleaf? I don't know. I cannot open overleaf. I don't know why. I cannot open. Why I cannot open it? I don't know why. I cannot enter the overlay. Why? I don't know why I cannot open it over here. Okay, anyway. Okay, let's resume. Fine. So if you use this method, so I think I should you can go back of this one. This one now you get that you have phi mu one equal to mu L of x1 phi mu one to mu L x2, then this will give you x1 2 times delta 1 delta 2 and the sim I mu1 is x1 minus x2 I mu L x1 minus x2 and times constant. That's what you get from this method. Another interesting example is 3-point function for scalar tensor. This is another interesting application one can consider. So suppose we have the following operator, one capital X1, O2 capital X2, and O L capital X3, and you just consider the following correction function. And here again, we assume this one is okay. Maybe I should write down M1 dot ML. So rank L, symmetric, traceless tensor, primary field. Okay. Then what you get is as follows. So again, this conformal inversion. So under scalar transformation. I is just goes to lambda xi. So from this behavior, this part is fixed. So this part is fixed. Okay, and what is the numerator? So now numerator will be affected by this the indices or higher spin. And then here it should be again some tensor depending symmetric traceless. So this is rank L symmetric traceless rank L traceless tensor. So it should be involved. But now we already know that what we should use. So we should use this one. So we should use this condition to determine, and then it should be the representation of the Lorentz group of SOD plus 1, 1. And the canonical choice to create such a operator, tensor. So suppose, so number 4 condition will tell x3 and I are and 1 total and L for I is 1 to L. Okay, so that's the projective this condition. And then, so therefore, so if you only suppose L is equal to 1, the tensor we can consider is the only tensor we can construct is false, which is the okay, so this is the invariant under the order. So this is, first of all, this is invariant under order transformation of this one. Invariant under the. So for instance, if you look at the degree of x1, degrees of x1 in denominator is 1/2 here, and it's 1/2 plus 1/2. 1/2 here, so therefore degree is 1 in denominator. And if you look at numerator, degree is 1 here, degree is 1 here. And also, so if you exchange the, and also this is the symmetric under exchange between x1 and x2. Symmetric. Right. So if you exchange x1, x2, of course, denominator is invariant. Here becomes x1, okay? x1 to x3, and x2 minus x. It's not the anti-symmetric. Sorry. Is that okay? Sorry. There's something strange here. It should be symmetric under the exchange of x1 and x2. That's what I thought. No? Somehow you get the negative sign. Maybe that's okay. That's how it is. Why is that? Let's see. Yeah, I see. Now I understand. Sorry. So it should be symmetric. Sorry. But this one is okay. Now I understand. Sorry. So this condition is not necessary, but later it's going to be important. So here, when L equal to 1, so this is the Rm is invariant. So first one is invariant. Okay. So now think is that it behaves as a vector transform as a L equal to 1, spin 1, rank L, so rank 1 for spin 1 tensor. And furthermore, you can see that the x3 dot number 3 is the important thing. x3 dot n Rm is equal to 0. So you can see that thing. Okay, so that's why you put this condition. So if you put like this way, then numerator cancel becomes 0. So left this one cancel. This is 0. So therefore, this Rm behaves this transverse condition. So therefore, if you consider such an operator, this Rm should be symmetric of this operator, Rm1. So here it just takes a symmetric trace part of these indices. Okay, symmetric trace part of these indices. Then transverse condition and Lorentz invariant and satisfied. So now we can pull back. We can pull back of this tensor to the Poincare section. Compensation. So if you do the pull-back, is the R mu is again capital X m, small x mu, and then R m. And then we know that this one will give you the following identity. So the x23, x13, and then x12. Okay, then minus x23. So that's what you get from this. Is it okay? Can you see that? So let's see. So here, so this one should be something like x12, x1. Sorry, if you read it like x13, x12, x23 times x23 square. Right? x13 minus Am I doing something strange, stupid? And then here x1 3 square and x2 3. Let's see, if you multiply them together, what's going to happen? Sorry, it's okay. So something strange here, right? Sorry. So it's okay. So they should be okay. It's consistent, right? So is this equal to this one? Is it okay? So let's do that. So this one is x1 2, x1 3 squared, x2 3 squared. Okay, and then this one is x2 3 cubed, x1 3, x1 3 mu minus x1 3 squared, x2 3, x2 3 mu, right? And okay, so you get rid of this one. You get rid of this one, and then you can erase these two. Why did I make a mistake? Sorry. So let's do it again. Square cube x1. Oh, it's okay. My brain's not working. So sorry, x2 3 cube. So it's okay. It's okay. And then if you get rid of it, this becomes square. This is square. Okay, it's okay. It's okay. So this is okay. So this is a pullback of this one. And plug this one into here. Okay? And what you get is as follows. 5 from x1, 5 to x2, and 5 mu1 total from mu L, x3 is equal to C1 to O. x1 2 delta 1 plus delta 2 minus delta 3, and then plus L, and then x 2 minus L, and x3 1 delta 3 plus delta 1 minus delta 2 minus L, and the same V mu1, V mu1. And then Z mu L is this one. Z mu L is, I define this one to be Z mu. So the shift of plus L here and minus L here coming from here. So this shift comes from here. Who give you this shift? That's the shift. It's really coming from here. Fine. So now let's look at the symmetry x1 and exchange of x1 and x2. Okay, 1 and 2. If you just swap 1 and 2, let's see what's going to happen. 1 and 2. Then, as you can easily see from this definition, everything here, you will get the z goes to, if you exchange 1 and 2, minus d1, d mu. Okay? So therefore, for when L is odd, so if you swap x1 and x2, so what you get is the so therefore what you get is the so C1 to O is minus 1 to L C to 1 O. So that's what I mean. So this is the exchange. So from here, from Z, you get the, if you exchange 1 and 2, as you can see, if you exchange 1 and 2, you get the minus sign. Really, minus sign. Since L of Z are here, overall you get the minus 1 to the L. But here, the quotient also needs to be swapped. Okay? So 2 and 1. So that's why the relation must hold. So this quotient should hold this relation. In particular, if this operator and this operator are the same, if this operator and this operator are the same operator, so then, all the odd rank symmetric tensor with the correlation function all vanishes because of this condition. Okay, so this means that the immediate consequence is that if you consider the following object, so the same operator, O x1, O x2, and O mu1 to the mu L of x3, then this is 0 if L is odd. Because I mean, so this, if L is odd, if one and 2 operators are the same, even if you exchange, the coefficient should be the same. Therefore, the coefficient should vanish. So this is the immediate consequence. Okay. So that's how we obtain the three-form function by using this embedding space-time method. One of the most important trace symmetric traceless operator, parallel operator, is what? Yeah, is equal to T mu. So let's consider the following thing. So if you consider O1, X1, O2, X2, T mu, X3. And this one is equal to some coefficient 1 to O, symmetric of Z1, Z mu, Z mu, okay? And then X1, 2 delta. I think I'm doing something. Yeah, I think what's written change. Delta 1 plus delta 2 minus 2. Oh, it should be okay. Like this one. And then x23 is the delta 2 plus minus delta Okay. Sorry. So what's the conformal dimension trace energy momentum tensor? Okay. So conformal dimension delta 3 is equal to D. Okay. So therefore it should be minus D minus 2. So therefore here should be plus D minus 2. And then here x31 is the delta 1 plus D. Okay, so that's should again. Okay. But however, we have some condition for energy momentum tensor. For instance, this should vanish. Because of conservation law. Okay. This should vanish because this guy is the descendant. No, descendant, so singular vector, sorry. Singular vector. So this should be equal to 0. So then this will impose the condition of the distance. Delta 1 has to be equal to delta 2. If you apply this numbers x3 derivative on here, you get this condition. So therefore, this means that the operator should be the same. So the operator should be the same. So then, so this becomes 2 delta, and this should be just d plus 1, d minus 2. It becomes d minus 2, and this also becomes d minus the exponent becomes 0. So that's the consequence of the singular vector of the coming from stress energy. Okay. So this is the consequence of the stress energy. Okay. Any question at this moment? Okay, so this is the power of conformal invariance. So we don't use any Lagrangian sum. We just use conformal symmetry to fix the correlation function. And then, in particular, if you consider the correlation function with stress energy tensor, we can just fix the form of the three-point function from this law to this law. Okay. Any question at this moment? Okay. 40 minutes left, and then one more lecture. My original plan was to talk about the conformal bootstrap. Of course, conformal block and conformal bootstrap, but I don't think I can go as much as I wanted to. But okay, let's talk about a little bit about the conformal block. Okay, let's talk about a little bit of the conformal. So far, we only talk about the three-point function up to three-point function with some spin and so on. By using the conformal symmetry, we can just think about the conformal block in higher dimension. So let's look at the four-point function or primary field in higher dimension. So that's not. So now let's talk about a little bit of conformal block, four-point function. and the conformal block in high dimensional field. That's okay. So in conformal symmetry, so in your homework you already showed up this one. All primary. This will be fixed by the conformal symmetry. So that's you already showed up the under the conformal symmetry, and U and B are cross ratio. So U and B are cross ratio, which I think you already knew how to write down. Maybe I can write down again. So the cross ratio is something like I don't remember. 1, 2, squared, 3, 4, and then 1, 3, squared, 2, 4, squared, and then x1, 4 squared, x2, 3 squared, divided by x1, 3 squared, x2, 4 squared. So these are cross ratios. This. So those are conformal symmetry determinants. Now we have a bit more knowledge about this four-point function and OPE and so on. Let's see what we can tell us about this GUB. Okay. So now let's do the following decomposition. So this. This thing. Okay, and then we know the OPE of O1, two primary fields have a following the expansion of the so A is primary. Like this. So around here, you have OK. Yeah, I mean, so C1, 2A in here. And then it's the conformal family of OA. And here, conformal family of OB and C3, 4B. So namely, we can just write down. The similar thing for 3, 4 part by using the other primary field. So similar thing can be done. So this I just write down. I'm lazy, so let's use the 3, 4b, and then 3, 4, and b, and b. That's the yellow part, which exactly what happened to me here. So therefore, so this correlation function, 4-point function, O is in fact can be obtained as follows. And then sum of A and B are primary, and then 1, 2, 3, the x1, 2 down down 2, and then C 3, 4, B, x 3, 4, and now log del 4. Okay, and then we have 4A, x2, 4B, x4. So like this. Okay. And this can be written as the so here, if you have a 2-point function, what is the constraint? No vanishing constraint should be what? So the conformal dimension needs to be same. So therefore, you have an x2, 4 to delta. So A, 1A, B, then x2, 4. So this is the formal version, the 2-point function. Okay. Then according to, sorry. And this can be written as follows. So this can be written as the, according to the, what we learned is that the, so essentially x1, 2, down 1 plus down 2, x3, 4, down 3, and down 4 over times sum of operator C1, 2, 4, C3, 4, 4, G, delta O, delta O. Okay, so that's the form. Okay. That's the form of this. So here, here we assume that the G of this one is really described as following the O1 of x1, O2, x2, O3, x3, O4, x4, and then here you have the some operator O, whose conformal dimension is O and spin is L. Spin is L. Okay. So internal channel you have some operator. It's not primary field, the infinite many descendant. And then but here we just need to write that. Okay. Okay, so that's the case. So and then we call whole quantity. So O is not necessarily all operators. This one is equal to G U B in upstairs. And GUB can be computed by using this method. Times distance. Okay, so that's the control block. And for instance, some of them are already known very well. Let's see. So this high-dimensional conformal field, conformal block, has been studied by a pioneer paper by Dolan and Osborne. For instance, if you consider the following thing, so if the all the so for I are the scalar operator, primary operator, with the conformal dimension delta I is equal to delta small delta, then for instance the G. People just read my notation is something like a delta O, and then L is equal to L. O is equal to internal channel 0, and then so 0 means theta means the operator scalar. So delta 1 to delta 3 4 is 0. Is the scalar. That's what it means. Of U and P are very simple form. For instance, this one. And it's more like hypergenous series. Hypergenous series. N factorial, and then delta O plus 1 minus 3 over 2, M delta O to M plus M, then times U to M 1 minus E to the M. So this is the so this is what Dolan and Osborne. Dolan and Osborne found the expression. It's a very simple form, of hypergenous series type. So of course, as I mentioned, Xm is x plus 1, x plus 2. X plus M plus 1. That's the case. So it's really like a hypergenous geometric function. The main conformal block takes this kind of hypergenous function. So if you look at the denominator of this one, so this derivation, I'm not going to go into detail because it's complicated. So, but just if you accept this one, so this has a form when this is vanishing. Okay, so this has a form when this is vanishing for some integer. Or integer, so the form, it has a form. When delta O is equal to -1 plus b over 2 minus s prime, delta O is minus s is b minus s. So this means that if you, this is not the unitary. Of course, this is not unitary because delta is negative. And this can be positive. This can, depending on dimension d here. But this means that they exist. They must exist. The singular vector in this conformal family of this orbital. Well, this itself has the singular vector. So that's the okay. So I just tell you some property of this conformal block of and to compute the, so I don't think I have a time as, of course, today I'm not going to go into detail. Maybe next week I may use some slides to explain some, if I use slides, I can explain a bit faster. So important thing is that how to say? So one of the recent success of the conformal bootstrap approach is essentially what we try to show is that this one, O1, O1, O2, O3, O4 is, schematic as I mentioned many times. O1, O3, O2, O4. Something like this way. If you call it like this way, so this will give you the infinite many constraint of the conformal block. So I call it this one is conformal block, or this one itself is conformal block. So this one is conformal block. Okay. And then if you use this, if you can solve this infinite many constraint by numerical method, you can actually determine the conformal dimensions, and then correlation function. Correlation function. Sorry. Correlation function of the 3D active model. That's one of the recent success by Rich Goss, Simon Duffy, many other people, like almost 10 years ago. I don't remember when it was the paper. I didn't print it out that far, so maybe. So that's anyway. So those are the recent, yeah, I think more than 10 years ago already. success. So on surface of the 2D Eigen model, in 1944 is exactly solvable on surface of 1944. And after that, the people naively expect the 3D Eigen model can be solved similar way by exam. Many people have tried, but nobody has successfully determined this 3D-dimensional Eigen model. But finally, if you use this conformal bootstrap and a numerical method, and one can actually compute correlation function very, very high accuracy. Very high, which I wanted to talk about, but I don't think I have only one lecture left, so I can briefly talk about it. So Eigen model you can solve by Onsager. Sorry, does Onsager get a Nobel Prize? I don't know. To be honest, I don't think so. But actually, there is some Smirnov. Show up the Eigen model can be described at the critical temperature. Temperature can be described by CFT. Is CFT 2D. He showed a mathematical rigorous way to show that it has a conformal symmetry. So he got a phase math. And then, so if you can show that the 3D Eigen model has the same can be described as CFT by rigorous way in mathematics, you may be able to get the field model. You are young enough. I'm already over 40. I don't have any chance. But anyway, so the numerical method will tell you that if you assume conformal symmetry, you can find you can compute the correlation function by using conformal bootstrap. So that's the I think 2010-ish by Richkoff. Simon Duffin, et al. So that's what I want to explain, but I don't think I have a time. So I just give you some brief property of this conformal block. This 4-point function. So as I mentioned, so this dollar Osborne is around 2000 something. Around 2000. I don't remember that detail. Around 2000. And then suppose, okay. So in this here you can just have the so here in the intermediate channel one can insert the following expansions, sum of all the psi to the all, and then psi, so there's psi, and which is equal to sum of all, this is the primary, and then n and O. So these are okay, sum of n. equal to 0 to infinity. And this can be understood as the order descendant. Okay. And then sum of n and gn delta p mu I acts on the infinite many times. I think I should write down like this. Product of I and j is equal to 1 to n p mu I acts on operator O and O and then k mu I acts on it. So these are some orthogonal how to say orthonormal frame in this it's a Hilbert space. Okay. However, so I mentioned that this, so this norm can be norm for the some state, for some n. For some n, there must be some n and some O. This can be vanished. So this means that the singular state or no state, it is descendant no state. Okay. So now, so if you do the conformal block of if you expand it in terms of this, how to say, it's called the orthogonal states, or like, so this is the orthogonal state. So this conformal block here has a pole when it has the singular state. So therefore, you can write down like this way, roughly speaking. You can write down, roughly speaking, G, delta L, delta 1, 2, delta 3, 4, and U and B is roughly has a pole, this is a residue at the point A, delta minus delta A star, and G, delta 1, 2, delta 3, 4, SA star. Yeah, around the pole. Delta is delta A. Delta delta. So this is the common property of the conformal block. So what this means? As I mentioned, if you start with some operator O, whose dimension is some conformal dimension delta A, delta A star. Okay, and this is a primary field, and you encounter some singular vector at the point S. This is the say OA, and then OAS, singular vector. So if you apply the P mu several times, you encounter singular vector. And this singular vector, all the descendants also become null vector. Okay, so those are subrepresentation of conformal algebra. And this has the OA, delta S, S, AS, and the spin L, AS. Okay. So therefore, if you expand in terms of this internal channel conformal block, if you consider conformal block, so this kind of conformal block, so this is the operator OA, and then O1, O2, O3, O4. This has a pole at the delta, so it's schematic form, delta A star. Some residue, and then here you have around the residue, it should have this OAS, singular vector, O1, O2, O3, O4. So this is a singular vector of this. So this has a property of the conformal. And using this one can create so-called recursion relation of conformal blocks should satisfy. So which hopefully I can just write down the recursion relation. So this is the so therefore when you set the so delta is equal to exactly this value, it becomes infinity. So this becomes infinity. But this conformal block is zero. Okay, it's because the internal channel is singular vector, which is the OP is vanishing, which means triple function vanishing. So therefore, this is the this contribution is the zero, becomes zero. So therefore, if you compute this conformal block, it will give you lots of information when the singular vector occurs and which primary field contains the singular vector inside its conformal field. For instance, this is the example. Okay. For instance, this is the example. Okay, and I don't think I have time to talk about this. More precisely, I can just do the following thing. Yeah, I don't think I can write down in part, so maybe I think it's okay. At the beginning of this next lecture, I will write down some recursion relation. So just normalize this G in some way. So G satisfied. Okay, I'll be very schematic. R and alpha I will explain later, which has following form. So, conformal block can be expanded like this one. So, this is exactly the, this will give you recursion relation of this conformal block, because I mean here, I have to explain all the notation. What is the R, what is the alpha, and what is this overall factor and so on next time. But essentially it means that when it has the internal channel has the conformal dimension delta, there is some pole occurs when it has the singular. Okay? And then here is the function R. If you look at the function R, is R to NA will it has R to NA. So therefore, if you compute the if you want to compute all the R to the N here, and then so therefore, if you know this information, all the R to the N minus NA, if you know the function all the R to the N minus NA, you just bring this conformal block expression here, and multiply R to NA will determine high-order function Rn. So therefore, if you know this function in terms of delta L or alpha, plug in some part of R. If you plug that back into here, you get the higher order R contribution. So and you can solve the recursively of this recursive relation to determine a conformal block. So that's one way to determine a conformal block. So this is the recursion relation. So this equation relation really comes from when this conformal block has the singular state in the intermediate state. That is one way to determine. The other way is Casimir relate equation and so on, which I don't think it's only 1 minute left. So that's one. Next lecture, I will briefly touch on it and then move on to 3D IT model at the end, hopefully. That's the last lecture. Okay. So what do we learn this today's lecture? What do we cover? Today's content is what? Can we record? Huh? Yeah. So mostly embedding space method to determine the correction function of two-point function, three-point function with higher spin operator, and then we move on to the conformal. Okay, so let's stop here. If you have questions, just please let me know.
I think this question is like I mean, if you doesn't want to compare with the actually functional and the average is just factorize and we can use these like set up equation.
Yeah. It's very simple. Yeah. So, but of course, you need some initial data to solve this recursion relation. But once you specify recursion relation, one can solve. But important thing is that sometimes this is not singular pole. It becomes like a second pole in the even dimension. So that requires some change. That requires some change.